Welcome back, everybody. Today I'm going to cover lecture 10, which is on iterative methods to simultaneous equations. Here we're going to move away from just looking at linear equations to also including nonlinear equations. And as the name suggests, we're going to use iterative approaches to solving them. So we've already covered a lot of information about solving linear equations. We did Gaussian elimination. Then we spent a lot of time talking about LU factorization and then using this for matrix inversion, stimuli responses. We talked about matrix norms and matrix, how we can use those norms to calculate condition number and estimate precision of our solution. This is all we're going to really calculate on doing those type of elimination linear algebra approaches. Now we're going to step away and move into numerical approaches, particularly Gauss-Seidel and Jacobi methods. Then we'll talk about diagonal dominance and what it means for doing iterative methods, and then we'll move into our third topic, talking about relaxation, so how we can get improved convergence with iterative methods through relaxation. And then we'll talk about solving systems of nonlinear equations using successive substitution and Newton-Raphson. The first method that I want to talk about is the Jacobi method. So the Jacobi method is an iterative solution for solving our linear equation. Once again, taking in the generality, a matrix A times vector X equals a vector B. Instead of trying to solve this equations simultaneously like we did with Gaussian elimination or LU factorization, we're going to start with the guess instead of trying to solve it exactly from the get-go. So here's our plan. We're going to guess our set of x's, then we're going to iteratively solve for each x successively using sort of this iterative method. The plan is we're going to take if A is a matrix we can write out in the traditional way, right? We can start thinking of that matrix as a series of those linear equations. So we can transform each individual x into one specific equation in a 3x3 system. Right? So x1, right, if I write this out, x1, x2, x3, is going to be b1 minus a12, x2 minus a13, x3 all over a11. What you'll notice is I've included an extra little index here at the top called j. This is going to be the index over which each iteration is going to take place, right? So I can't write that. We used to write our indices right here below the x, but that's where we're going to keep track of which x we're going to use, which x we're solving for. So instead, I'm going to put my j in the upper right-hand corner. Right? And so the idea behind this method is I'm going to make three guesses: an old x1, an old x2, and old x3, and I'm going to calculate a new x1, x2, x3 using the old x variables and that simple linear solution equation. Right? I want to point out that when I'm using the Jacobi method, all of my indices for which x I'm using when I calculate x1, x2, x3 is going to be the previous x. Right? So when I calculate x1, I use old x2, x3. When I calculate the new x2, I use old x1, x3. When I calculate the new x3, I use the old x1, x2. We'll see why this is going to differ a little bit from the Gauss-Seidel method after we sort of finish the Jacobi example. So once I calculate this new x1, x2, x3, I'm going to go back and I'm going to start the substitution all over again. Right? So I'm going to go through, calculate my new x1, x2, x3, then I'm going to use that in the next round to calculate a new x1, x2, x3. Let's look at an example. Here I've written out a matrix A, a vector x, and a set of b's. And we're going to use our Jacobi matrix to solve this. First, we need to translate the matrix in conjunction with the linear equations into a set of equations for x1, x2, x3. I can do that by taking the various elements, so 3 for A1, 7.85 for B, negative 0.1 for A12, and negative 0.2 for A13. And I can convert this generic equation into an equation for x1. And I can do the same thing for x2 and x3. Once we have these individual equations, we just need to figure out what my initial guess for x1, x2, x3 are, because as we can see in that x1 equation, we need an x2 and an x3, and then the same thing for equations 2 and 3. In this case, we're going to assume that we're starting with zeros as my initial guess. So all I've done is I've taken the equation for x1 and I've written it here. Now, let's go in and fill in our solve out this x1 equation. So we have x1 equals 7.85 plus 0.1 times x2, which was 0, plus 0.2 times x3, which was also 0, over 3. If you do out all that math, you get 2.61666 repeating. Okay, so this is going to be my new guess for x1 in the second round. I'm then ready to solve for x2. Here, I have my equation already set from earlier, but I'm ready to do, but I need my x1 and x3. In the Jacobi method, x1 is still going to be 0 because we're using that old guess, and x3 is obviously still 0. So if I solve this out, we have negative 19.3 minus 0.1 times 0 plus 0.3 times 0 all over 7, and this comes out to be negative 2.75714. Right? And then we can do the same thing for x3. I'm not going to go as in depth through here, but once again we're going to use the 0 for x1 and 0 for x2 because we're using the previous guess. This is going to be 7.14. So when all is said and done, we end up with a new guess vector for x1. Here, all I've done is I've collected those 3 different terms and put them into a single vector. So this x1 vector, which is the x vector after one iteration, remember that top mark is standing for which iteration I'm on, is now ready to move forward. So now I'm ready to do x1 again. Here I'm going to still use my x1 equation, but now I'm going to use the x2 and x3 from my my first iteration of the x's instead of 0. So let's do this out. I have 7.85 plus 0.1. My x2 guess is now negative 2.75714. plus 0.2 times my guess for x3, that's 7.14, all over 3. And that's going to give me an x1 guess in my second iteration of 3.0007. Okay. Now I'm going to go ahead and do that again, but now with my x2 equation, remembering that x2 is negative 19.3 minus 0.1 times x1, we're going to pick the previous guess for x1, so that's 2.61666. Then we move on to our x3 term, 0.3 times x3, well, that's 7.14, all over 7, and this gives us an x2 value of negative 2.48852. Okay. Now we're ready to move on to x3. We're going to use our x3 equation and x1 and x2 from our first iteration of the Jacobi method. So we have 71.4 minus 0.3 times x1, so that's still 2.61666 plus 0.2 times x2, which is negative 2.75714, all over 10. And that gives us an x3 value of 7.006357. Okay. So now we can update our x vector. Here we can tell that we're on iteration 2, or j equals 2, by that 2 in that above the x. Be careful when you're doing Jacobi that we don't confuse that for an x squared, but that's, j equals 2, not to the power. Right. Now that we've done the third iteration, we could go ahead and, now that we finished the second iteration, we could go ahead and finish complete the third iteration, the fourth, etc. It gets a little repetitive very quickly, so I've gone ahead. That gets repetitive relatively quickly, so I've gone ahead and done that out for us. So here I have listed out the various j's, starting with my initial guess of 0, and then written out those x1, x2, x3 for each of those j's. And we can see that as I go down, I start seeing a convergence, just like we had with our root finding and optimization. We should be moving towards consistent numbers for each of our individual x's. Just like in root finding and optimization, we need a way to measure how well we're converging, and we can do that just using approximate errors, just like we did for optimization and root finding. So once again, we can use our approximate error. Here we have an additional subscript in our approximate error, this I, to let us know which of our x's we're talking about. And then, of course, we have our j representing which iteration number we're talking about. So I can go in and calculate my approximate error for each x1. So let's maybe write out, so the approximate error for iteration for x1 in moving from step 2 to 3 would be the new step 3 value, so 3.00072 minus 2.616667 all over that 3.00072 times 100, and that will give us the error. And we can look at the error at each of our different x's as we move down the column. Previously, when we were talking about root finding optimization, we only had one error to look at. But in this case, where we have 3 different x's, we need to look at the error for every single one. And we need to pick, and we can only say that our guesses have converged when every single one of those elements is converged. So even though, say, x1 is starting to look pretty converged on iteration 3, the x2 does not look very converged, right? We need to have all of our x's converge together to say that we're fully converged. The Gauss-Seidel method is another iterative method for solving systems of linear equations. The difference between the Gauss-Seidel and the Jacobian is that we're going to iteratively use the x's as we have them develop. If you remember before, we used 0, 0, 0 in when we calculated the entire set of new guesses of x's. Right, so in our first round through, we calculated some new x1. But when I went down to calculate x2, I used the previous value of x1. So I used, say, x0. Even though I know more about my system, right? I know what a better guess for x1 than I previously did. The Gauss-Seidel method is going to take advantage of that. What the Gauss-Seidel method is going to do is it's going to say, use the most up-to-date guess for x1. Use the most up-to-date guess for x. So when I solve for x1, I need to use my old guess for x2 and x3. But when I solve for x2, I can use my newest guess for x1 and then the old guess for x3. And then same thing for x3, I get both the updated guess for x1 and the updated guess for x2. So we can see that we have sort of this more rolling methodology. We know which values are going to use the updated guess of this round and which are going to use the old round by paying attention to the indices. So here in the Gauss-Seidel method for x2, I still have j minus 1 for 3, but I have j for x1. So I'm going to use my current round's x1 guess, previous round's x3 guess. And then once again, x2 uses the current round's x1 and x3. Right? So once I calculate x3, I can take that x3 value and go back and start a brand new round. We're going to go through the exact same problem that we had examined with the Jacobi method with the Gauss-Seidel method. So once again, I've written our A matrix, we have our X vector and our B vector written out, and then I've copied the set of equations that are going to govern x1, x2, x3. Remember that the difference being in solving for x2, we're going to use the value from x1, and then for solving x3, we're going to use both our previously calculated x1 and x2. So same problem, same initial guesses of 0, just a slight different implementation of the equations and what we use for x1, 2, and 3 as we go through. All right, let's start in. So as before, we have x1 equal to 7.85 plus 0.1 times our initial guess for x2, which is 0, right? Because it's our first guess, we're starting from 0. And then 0.2 times x3, which is also 0. All over 3. So just as before, we end up with 2.616667. Now the difference between this run and the Jacobi method is we're now going to use this 2.6166 So now when we start x2, we have that negative 19.3 minus 0.1. And here we're going to use x1. So we're going to use that 2.616667, not 0, right? 0 was Jacobian method. Now we're doing Gauss-Seidel. So we're using that new x1 value. Okay, so now we move on to this last piece of the x2 equation. So 0.3 times x3. x3, we don't have any better guess than 0, so it still goes in as 0. We put this all over 7, and when we calculate this out, we get negative 2.79452. Right, now we're ready to do x3. We still maintain that 71.4 minus 0.3. We're going to use our best guess for x1. Our best guess for x1 isn't 0. It's 2.616667. And then when we go in to do our 0.2 times x2, we use our best guess for x2. That's negative 2.79452. And then we put that all over 10. When we do this out, this is going to be 7.00561. So just as before, we can come up with our guess for our after the first round of Gauss-Seidel iteration. And we see that it looks a little bit different than we had for the Jacobian. We'll come back in a second to compare Jacobian versus Gauss-Seidel, but just keep in mind that we're going to use these new values for our second iteration. So as not to belabor the point and just spend a lot of time doing math, I'm going to sort of go through this next piece relatively quickly. So once again, we're going to take our different values. So x1 in the second round is going to be 7.85 plus 0.1 x2. x2 is negative 2.79452 plus 0.2 x3. x3 is 7.0056 over 3. That's going to give us 2.990557. We have round 2 of x2, which is negative 19.3 minus 0.1. Once again, we're going to use our new value of x1. And our old value of x3. And we can calculate that all out to give us our new value of x2, which is negative 2.49962. And then we can come back and get our last value for x3 using our new values for x1 and our new value for x2. Which will give us our new estimate for x3, which is 7.000291. And we can see already, if we compare our x1 Gauss-Seidel configurations to the second round, we're actually getting there quite quickly. So just as we did with the Jacobi method, we can take this, the Gauss-Seidel method, and do several iterations. I've written out the different iterations indicated by J along the side. What you'll immediately notice is after our second iteration, so all the way over here, As we move to our third iteration, we're essentially converged. And we can put some numbers to that by looking at the error. You see by the time that we're at our third iteration, we're already having errors that are less than 1%. By the time we get down to our fourth iteration, we have a very converged solution. If we compare this to the Jacobi method, remember it took us quite a few iterations more to end up with that nice round 3 for x1. And if we look at the error, to go down below, we just converge much slower. So after 6 iterations, we have 10 to the negative 6 times 10 to the negative 8% error versus only 4 times 10 to the negative 5th error after 6 iterations. So that Gauss-Seidel iteration converges much faster, which really shouldn't be a surprise, right? Because we're using, when we make our new x2 guess, we're using the updated xj, so we have a better guess for x1 to start with when we go on to x2. So while the Jacobi method is good to sort of know that Gauss-Seidel method is the much faster way. As with any iterative method, we have always the possibility that the method may diverge. And the Gauss-Seidel method is no different. However, we know that the Gauss-Seidel method will definitely converge if the matrix is diagonally dominant. What I mean by diagonally dominant is if I have a matrix, if the element along the diagonal of each row is the largest, it will converge, right? So in the second row, say the element in the second column, if the element in the second column is the biggest, that would be then the diagonal dominance check for that second row. We would check to see if that first element of the first row is the biggest number of the whole row. See, now we're not looking at columns, we're looking at rows. And same thing for the third row, that fourth row, all the way down. On top of looking for diagonal dominance for the certainty of conversion, and the fact that the Gauss-Seidel method is much faster than the Jacobian method, we still may be interested in speeding up our rate of finding the right answer. The way that we can enhance this convergence or enhance the rate is through what's called relaxation. What this is essentially going to do is try to predict more towards the convergence than we would necessarily get just doing that straight substitution. We're going to use this equation to try to preempt that relaxation. So here we have several terms. So we have our new xi, the xi that was predicted from the Jacobian or the Gauss-Seidel method. So this is GS or J predicted or calculated, sorry. And then we modify it, or we mix the new prediction and the old prediction using this factor lambda. So that lambda is going to be a weighting factor. Now, to prevent, if we want to increase the rate of convergence, we can do what's called over-relaxing the system, where we try to get a jump on that. Get a jump ahead. And we can also do what's called under-relaxing when lambda is between 0 and 1. So essentially we're retaining a little bit more of the old value. This one we retain more of the old value. And here we sort of not just move on to that new value, but weight a little heavier. We weight more on that new value. And so here, your selection of lambda is really going to dictate how well we're going to converge, or how fast we're going to converge. Let's put this into practice. Let's take a new example. Here we're going to solve the following system of equations using Gauss-Seidel with over-relaxation. So here, our lambda term is going to be equal to 1.2. And we're going to do this, well, as long as the error is greater than 10%. I've written out two equations that we're going to use to solve simultaneously. Notice they're not in matrix form, but we can put them into matrix form. So -3, 12, 10, -2. Equals 9 and 8. And more importantly, we can rearrange these to isolate x1 and x2 by themselves. So we can rearrange x1 from that lower level equation, x1 equals 8 plus 2x2 over 10. And we can put this in decimal form to help us out a little bit later. And then we can use pull x2 by rearranging that top equation, 9 plus 3x1 over 12. And then once again, we can put this into decimal form. All right, now that we have our equations set up, we're ready to conduct our Gauss-Seidel construction. Okay, so here I've just written out that x1 term, again. Remember, x1 is 0.8 plus 0.2 times x2. I've already included the fact that x2 as our guess was going to be 0. So our new guess for x1 is 0.8. Now, what we want to do is we want to use this equation, this relaxation, to help more predict or accelerate our prediction of our material. So we can go in and say x1, and I'm going to say r for relaxed is going to be lambda, which was 1.2. So I'll just write that in there so we don't forget. 1.2 times our new x1. So this is 0.8, right? So this is just going to come in there. Plus 1 minus lambda, so 1 minus 1.2, times the old x, which was 0. Right? So when I do this all out, I have my new guess for x is 0.96. What we'll notice is this relaxation is predicting that x1 is going to be even bigger than the x1 that we get strictly from Gauss-Seidel. And we're moving farther, or we're moving faster away from that initial guess. We can do the same thing with x2 and say x2 is that 0.75 plus 0.25 times 1. Well, we should use our best guess for x1, so that's that relaxed value. I'll just drag that down here, times 0.96. And that's going to give us our new best estimate for x2, which is 0.99. Once again, I'm going to relax that case, and so to find an improved guess, so that's 1.2 times our new guess, 0.9, plus 1 minus 1.2 times the old guess, which was, of course, 0. And this gives us a modified guess of 1.188. So you see, in both cases, when I compare the two, I'm moving faster away from that initial guess of 0 than I was if I just done strict Gauss-Seidel, right? So hopefully this is going to get us to our solution faster. So we can continue on to the second iteration. I've pulled the relaxed x2 value forward, and we can then continue on with our new guess of x1. Just in the interest of time, I'm not going to do out all the math with you, but I'm going to just comment on it. Here we're still doing Gauss-Seidel, so when I pull this x1 equation down here, I'm going to use my new guess for x2, so that 1.88. And so this is going to bring us to 1.0376. Already we can see that we're starting to converge relatively quickly. Once again, I'm going to perform relaxation on that using 1.2 as my lambda. Here's my new value. My new value for x is 1.0376. And I take that old guess for x, 0.96, in that term there. Right? So once again, we're going to get a boost in our x prediction, this time of about 0.2. So you can see that we're getting a smaller boost before we had 0.1 increase via relaxation. And so now we're starting to, that jump ahead is shrunk. When we look at calculating our error, we're still going to use the relaxed values. So we're going to use that 1.05 for the current guess, and then 0.96 for the old guess. We don't use the unrelaxed value, right? We're going to use the previous value. Right, so then this is going to give us an approximate error of only 10%, of less than 10%. Great, that was our goal for x1. So we're feeling good there. Now we can come in and we can start in on x2. So we can pull down the x2 equation and then use our best estimate for x1. So this 1.053 in our x2 equation to predict a new x2. So that's 1.01. And we can use relaxation once again to get a new enhanced value. This time, because our old value was 1.18 and our new value is 1.01, that relaxation is actually going to bring us back closer to 0. Right? We're going to move backwards a little bit, or move closer to 0 more with the relaxation than we would with just x2. Once again, we can go in and convert the error. Unfortunately, this time our error is bigger than 10, so we have to do a third iteration. All right, so I can pull my equation for x2 relaxed forward, and we can start this process again. So I can go through, calculate a new x1. I end up with 0.98, which is going to give us an error of 7.01. And I can use that 0.98 to calculate a new value for x2 using Gauss-Seidel. Use relaxation, and here you can see that the relaxation is hardly changing these values at all. This is a good indication that we're converging, right? Because we're looking at these differences in numbers. And indeed, if we look at the error estimation for our second x, we're now down to 2. We're converging, our error is below 10, so we can say that this system is good to go. Overall, hopefully this illustrates the fact that using over-relaxation, we can try to jumpstart and get faster convergence than without over-relaxation. We can go the other way. We can use under-relaxation, so we mix in a little bit of our old value, and this may help with convergence if we have diverging solutions. The last category of simultaneous equations that we're going to cover are nonlinear systems. So these systems are are like linear problems, but now we have nonlinear terms in them. We have some sort of form where x isn't just by itself times a constant. So these can be solved using the similar strategy as the Gauss-Seidel method, where we solve for a system of one unknown and we update each value as we go. This is called successive substitution. So we'll go through that first, and then we'll talk about a different method. I also want to say that we can solve these problems using fsolve in MATLAB and the Excel solver program in the solver in Excel. We'll talk about this a little bit when we get into our Excel mini unit. So let's go through an example nonlinear system. Here I've written out a system of nonlinear equations. x1 squared plus x1 times x2 equal to 10, and x2 plus 3x1 x2 squared. You can tell these are nonlinear because in the first case we have a squared term. In the second case I have my x1 times my x2. And this is sort of similar in that second case. Here I have an x2 squared times x1. Right, so we know that these are nonlinear. I can graph out these two solutions, and we can see graphically where we expect our solution. Right, that solution is going to come where I have the crossing. The idea with successive substitution that we're going to cover in a second is we're going to convert each of these two equations so that we have x1 equals to some equation on one side and x2 equals some equation on the other side. So going all the way back to those root finding ideas, we want to rearrange these equations to isolate x1 on one side, x1 on the left-hand side of one equation, x2 on the left-hand side of the other equation. And then if you had multiple or more x's, you would want to isolate each of the different variables on the left side. And then we're going to go just like before with Gauss-Seidel, where we'll make some guesses. We'll use the new estimate for x1 to estimate what's going to happen in x2. And then we'll use x2 to re-estimate what's going to happen in x1. So let's take a series of these. Let's solve these out using successive substitution. Here we're going to start with a guess of 1.5 for x1 and 3.5 for x2. So the first job is we need to isolate x1 from that first equation. So we can say x1 squared plus x1 x2 equals 10. So I'm going to isolate this x1. So we get x1 equals 10 minus x1 squared over x2. Right? I could have done this the other way, isolating x1 from the x squared, and we're going to see what happens if we do it both ways. So now I can isolate x2. This one is a little more straightforward. I can just move that 3 x1, x2 squared to the other side. We get x2 equals 57 minus 3 x1, x2 squared. Now we're ready to start our successive substitution. Remember, we wanted to start with x1, with our guess of x1 equals 1.5 and x2 equals 3.5. So just like Gauss-Seidel, we take our equation for x1. In this case, it's 10 minus x1 squared. So 1.5, so I've put that 1.5 in there, squared over 3.5, and that equals to 2.2 with some other trailing behind it. I can then take this equation, this new guess for x1, and I can write out a new equation for x2. So that x2 is now going to be 57 minus 3 times x1, so 2.21429, times x2 squared. Remember, our x2 guess was 3.5 squared. And you can do out that arithmetic and you'll get negative 24.375. Okay, so great. This is now the end of our first step. So we can go in and do this step, the second step. So once again, we can write out our x1 equation, 10 minus x1 squared, so 2.21429 squared, over our x3, which was negative 24.375. I do out my math, and I end up with negative 0.209. Right? So we can do the same thing for x2. Plug this in, 57 minus 3 times x1, so that's negative 0.209 times x2. What was our previous value of x2? Negative 24.375 squared. This ends up being 429.709. Well, we're in trouble. If I look at my answers, you'll see that we're starting to diverge. My guess for x2 was 24 after the first round. Now I'm at 429. So I went from 3.5 to 24. Okay, that's a change of 20. Now I went from 24 to 429. That's a change of 400. My guesses for x2 are getting further and further apart. This is going to show us that how we choose this equation matters. We need to go back and rearrange these equations a second time to put them in a different form that hopefully won't diverge. Let's try this form. I've taken those equations and I've rearranged them now using this x squared term, keeping that one on the left, and moving this x1, x2 to the right. When I take care of that square root, I get x1 equals the square root of 10 minus x1, x2. Similarly, I'm going to now keep this x2 that's squared on the left and move the other terms to the right, giving us the square x2 equal to the square root of 57 minus x2 over 3x1. We can now start our iterations again. So let's start with x1. x1 equals the square root of 10 minus x1, which our initial guess was 1.5, times 3.5, which was our initial guess for x2. This gives us 2.17945. If I punch my numbers into the x2 equation, we have 57 minus 3.5 over 3 times 1.5. If I do this, I get 2.86 as my x2. Already this is starting to look better. I haven't meandered that far off my initial guesses. I'm going to now go in and do this for a second time. So we have x1 equals the square root of 10 minus 2.17945 times my new guess for x2, so 2.86. When I put this together, I get 1.94. Now if I do the same thing for x2, 57 minus 2.86 over 3 times 1.94. My next round for x2 is 3.04. The nice thing is I've gone in terms of x1, I had 1.5, then 2.17, then 1.94. Right? The differences as I'm moving from one step to the next are getting smaller. The same thing is happening in x2. I started from 3.5, I then went to 2.86, and then 1.94. The differences between my individual steps are getting smaller. We're converging. This is going to show us that which x1 and x2 we pick to put on the left-hand side is going to change the stability of the solution. We can go from being a convergent solution like we see with these pairs to a divergent solution like we saw with the other set of pairs. Similarly, even if it doesn't make a diverging solution converge, we can move to a case where it affects the speed. So if I have one set of x's, we may converge more rapidly. Right? So in general, it's a good idea to keep to use those to get rid of those high order exponents, just to try to keep that derivative of your solutions less than 1. Last topic I want to talk about for this unit is using Newton-Raphson methods for solving simultaneous nonlinear equations. Just like we use Newton-Raphson to solve root-finding methods, we can use a Newton-Raphson method in solving simultaneous problems. What we're going to do is we're going to have our function 1 and our function 2 written out. Then we're going to do a series of Taylor expansions around that solution. So if you recall, we can say that an estimate for any movement off of a point is the value at that point xi that we were at plus xi comma j plus 1 minus x1i. So the value that I'm currently at plus the difference in my x values times the derivative of my function with respect to x1. And then in the case of having a multivariate problem, we take the change in value of my x2s times my partial derivative of that function with respect to x2. I can write the same thing for my secondary function, shown down here, where I'm looking at my new guess for my function 2 is my old guess or my old value of the function times my change in x1 times the derivative of that function with respect to x1 plus the change in my value of x2 times the derivative of the function with respect to x2. I can take these two equations and rearrange them to isolate x1 and x2, right? So if I take this equation, I can rearrange to isolate it, and I end up with this equation over here. So my new value for x1 is the old value of x1 minus the original value of function 1 with respect to I times the derivative of the second function with respect to x2 minus my current function value of the second function times the derivative of the first function over x2, all over the derivative of function 1 with respect to x1 times the derivative of function 2 with respect to x2 minus the derivative of function 1 with respect to x2 times the derivative of function 2 with x1. You can get a similar but slightly different form for x2. What I want to point out is this at the bottom is the determinant of the partial derivatives, f1, partial f1, partial fx, then partial f1, partial x2, partial f1, partial f2, partial x2, and then partial f2, partial x2. This will come back in a second. We can write this in this form of this determinant and call this our Jacobian. Sorry, the determinant of the Jacobian. Here, our Jacobian is a matrix of partial derivatives of functions. So here in the columns, we have partial with respect to x's, varying x's, and then in each row are the different functions. Okay, so just like we had before in the traditional Newton-Raphson, where we said each xi plus 1 equal to xi minus f of xi over the derivative of xi, we can write an equivalent functional form of the multi-dimensional Newton-Raphson, where we have xi plus 1, a vector of xi plus 1's equal to a vector of xi's minus our inverse of a Jacobian times our function values at those xi's. Let's put this into practice and we'll see how this is going to work. Let's look at the same system that we did with successive substitution. Here I have my same x1, f1 and f2 equations sort of written out. We'll have to modify them to be the right f1 and f2, but we'll put them to rights in a second. And then over here, I've got my definitions for my updated values. So let's start. So the first thing that we need to do is we need to calculate the Jacobian. So this means we need to come up with all the partial derivatives for my system. So let's look first at f1. So if I call this first function f1 as I did on the previous page, and I take the partial derivative with respect to x1, the partial derivative of x1 squared with respect to x1 is 2x1. So I can just write that in here. And then the partial derivative with respect to x1, x2 is just x2. We would necessarily have to move this sort of over to create that real function, but when we're taking the derivative, it doesn't matter because it's a constant. I then want to come in and I want to look at that value of the partial derivative at the states that I'm at. So I need to put in these hard numbers. So we can say 2 times x1, remember our initial guess was 1.5, plus x2, and our initial guess was 3.5. I can sum these up and we get 6.5 as my first partial derivative value. Next, I can do the same thing for the partial derivative of f1 with respect to x2. If I once again look at this top equation, take that partial derivative of f1 with respect to x2, that first term goes away and I cancel out that x1. I cancel out that x2, right? So I'm only left with x1. Well, then computing this is easy because our guess is 1.5. We now need to take the derivative of f of x2. So we now need f of x2 first with respect to x1. Well, there's no term, x1 term in the first term, and I can now drop it from the second term, leaving my partial derivative with respect to x2 as 3.x2 squared. I can go in, take that, put in my guesses, so 3.5 squared. This gives me an answer of 36.75. All right, and then we need the derivative of f2 with respect to x2. That's 1 plus 6 times x1 plus x2. I can go in and calculate this, as 1 plus 6 times 1.5 times 3.5, and that equals 32.5. Right. So I needed my 4 values for my Jacobian matrix. I now have my 4 values. I'm ready to punch them into my Jacobian. So here are the values. I've just taken them and I've put them into their matrix form. Remember to take that determinant, which we need for the bottom half of that case. I take 6.5 times 32.5 right here, minus 36.75 times 1.5 here, and I end up getting my determinant value is 156.125. So this is my determinant of my Jacobian. Now that I've finished determining my determinant, in essence, calculating the bottom half of these two denominators, I'm ready to tackle the top half, right? I need the values of the functions at x1 and x2. So not to belabor the math, but I can take my equations for x1. Remember, we had x1 squared plus x1 x2 equal to 10. I need to get that in the right functional form, so that transforms into this form of f1 by moving the 10 onto the right side, and then we move that move the 57 onto the left side, so we have everything sort of bunched up in one set of terms. I can then go in, plug in my guesses for x1 and x2, and calculate my functional value of f1 at my 0th guess and f2 at my 0th guess, being negative 2.5 and 1.625 respectively. I'm ready to move on to step number 3, which is going to be determine my individual x's. I have everything that I need. I have my old guess of x, I have the function, I have my derivatives, and I have the determinant. So I'm ready to go. It's now just an exercise in plug and chug. I'm just writing down that determinant value here so that when we come to write it out, it's easily at hand. Okay, so for the x1, comma 1, we have the old guess for x1, which was 1.5, minus f of the value of f1, so that's negative 2.5, right? So I'm going to pull that down here, times my derivative, so that's that we now need this piece, that derivative of f2 with respect to x2. If you remember from the previous slide, that's 32.5. Now I need the function value of f2. In this case, that's 1.625 times the derivative value, which was 1.5 from the previous page, all over that Jacobian value of 156.125. All right, this is going to give us 2.03603. Now I'm ready to compute the value of x2. I have my old value of x2, which is 3.5, minus now I need the value of f2, that's 1.625 times the derivative of f1 with respect to x1. If you remember from the previous slide, that was 6.5, minus the function value of f1. Oh, well, from up here, that's 2.5 times the derivative of f2 with respect to x1. So from the previous slide, that was 36.75, all over my Jacobian value of 156.125, giving us a value of 2.843. Now that I have this, my new guesses for x1 and x2, I'm ready to repeat. What do I mean by repeat? Well, I need to go back and calculate my partial derivatives values with these new x's. I need to calculate my new function values with the new x's, and then I can go ahead and calculate a new set of x1 and x2. Just like with the old Newton-Raphson, I'm just going to do this again and again until I get a converging solution. And we can use approximate error in order to estimate how converged we are and how many iterations we need. What you might be saying to yourself is, this is a problem because I need to know the functional form of my I need to know an analytical derivative. And that's true, right? We need to fill in this Jacobian matrix for doing these calculations by knowing what that derivative is with respect to x1 and x2. But sometimes it may be very difficult to solve that analytical derivative, or you may want to have a function that's going to work, a routine, say in MATLAB, that's going to work on any function or series of functions without actually doing, without actually having to go in and type out that analytical function. This is where perturbation theory can come back. If you remember from talking about the modified secant method, we could determine via perturbation theory what that derivative is, or in this case, what the partial derivative is. Right? I can say that my partial derivative of f1 with respect to x1 is the function value of x1 times x1 plus delta x1, right? So that delta times x1 is my perturbation, and at value x2 minus f1 of x1, x2 over what that perturbation is. And I can do the same thing for my partial derivative with respect to x2, being the function value at x1 and x2 plus perturbation times x2 minus f1 of x1, x2 over delta x2. This way, I never have to have an analytical form to my for my partial derivatives. I can do these analytical or these numeric forms of the partial derivative in order to get what those values are. Once I have these four values, I can take them and plug them in to the appropriate location within that Jacobian. And once I have that Jacobian matrix from perturbation theory, I'm ready to move on and complete the Newton-Raphson method for simultaneous nonlinear equations. All right, that's going to wrap up all the content for Unit 3. In review, we've covered the Gauss-Seidel method and the Jacobi method. Remember, the difference being in the Jacobi method, we use all of the old guesses. In the Gauss-Seidel method, we update the values at each individual step. We talked about diagonal dominance and said that if I have a diagonally dominant matrix, I'm guaranteed to have conversion with the Gauss-Seidel method. We then employed relaxation to improve convergence and the rate of convergence. And then finally, we talked about solving nonlinear equations with successive substitution and then with a Newton-Raphson method. This is going to end chapter 12 and wrap up our unit on simultaneous equations. As we move into the next class, we'll move on to a new chapter on fitting curves. All right, see you in class.